Hey guys, what's up? Eddie Aho here with KissAnalog.com. Well, today what I want to do is I want to show what a switch mode power supply for an AC to DC power supply would look like, okay? I have two evaluation cards here that I'm going to use to demonstrate this, and it's going to be pretty cool, I think. So we're going to just get in this video pretty quick. A lot of the video is going to be testing, showing signals, and showing what these boards do. So let me just kind of explain why we might want to have a switch mode power supply. We've been looking at this Class D power supply, right? And pretty cool, but it has a big old transformer, a bunch of capacitors there, and so you got all this efficiency of the Class D amp, but then you have a linear power supply. And what's the problem with that? Well, big old transformer for one. The other thing is power factor. The transformer has to be even bigger than the rated power because the power factor issue. The power factor issue, it's where we have reactive power. It's power we're bringing in. We're not dissipating it. We're not using it for our load. It's just cycling through the power system and going back. It's the current voltage being out of phase, out of time with each other. And so the current and the voltage don't line up together. You don't get the peak current voltage at the same time, so you end up having to have more current than you need. That's just turns into reactive power, and it's cycled back out. So your transformer and input circuitry has to be able to handle that higher current. Well, and then again, we go back to the weight. Another thing is, people say, well, switch mode power supplies are noisy, but so are linear power supplies. They have bridge rectifiers. Those diodes are turning on and off. They're commutating. That creates some noise too. A little different noise, but anyway, that noise is part of, it goes into the bucket of power factor. It's part of the power factor equation, and so that's just unusable power. So that just doesn't really help us. Okay, so with the linear power supply, we have the big old caps, the big bridge rectifier, and that's for an audio amplifier too, and these toroid transformers, right? With this switching power supply that I have here, let me get my board and I'll just go through it real quick so we can get to the test. Alright, so let me just compare the linear with the switcher. Okay, with the linear we get the isolation, the galvanic isolation, meaning there's no DC connection, or there's no continuity, no ohms connection between input and output. Okay, so there's that galvanic isolation. So we have a transformer, we drop the step down transformer usually, and for an audio amplifier we'll have at least two outputs plus minus supply rail, right? And they'll go through bridge rectifiers, and then we get a DC. So we got AC to smaller AC to a pulsating DC, and then we use a bulk capacitor to smooth it off, and we get some ripple on top. And then we got our AC to DC power supply. With the switcher, we're going to put the bridge rectifier right up front, and then so we're going to go AC to pulsating DC, and then with the boost converter we're going to boost that voltage up to high voltage, around 400 volts, 390 volts maybe. And the reason we have to do that is, we don't have to, but if we're going to make an AC power supply that's kind of automatic, so you don't have a switch where you have to switch it back and forth, we're just automatically will take, say, US power and power over in Europe. Say you're going to operate from 85 volts in all the way up to 265, 285 even. Well, you have to look at the peak value of that voltage, and then you have to make your DC power higher than that, because it always has to be boosting. Alright, so you boost it, then you put a storage capacitor, now you got your DC with ripple, and then you go through a switching power supply where you get your isolation and you get all the voltages you want depending on. So this transformer, the symbol might look very similar to this, could look very similar, but it's going to be much smaller. In the linear, he's operating on, say, 60 hertz here in the States, so the magnetic field's building slowly and then dropping, but as it builds it has to withstand that energy for a long period of time, so it's a volt second thing. And over here, let's say that's 60 hertz, and let's just say this is 60 kilohertz. It's probably going to be a lot faster, but let's say 60K, that's 1,000 times faster. So if you're 1,000 times faster, you don't have to store that energy very long. You're transferring energy, coupling the energy, the voltage, from one side to the other side in quick little buckets. Versus up here, you know, big old wheelbarrows. So this guy's going to be huge compared to this guy. The other thing is this bulk capacitor is going to be large for the same reason. It's going to smooth off these humps on this pulsating DC, which is, now it's 120 hertz over on this side, but that's still slow, so it's got to hold it up until the next pulse comes along and charges it again. Down here, this guy, it's operating very fast. So instead of this guy dumping big old wheelbarrows of, you know, juice into the capacitors, this guy's throwing a bunch of small cups. You know, a bunch of guys standing in line with Dixie cups just filling it up. So it doesn't have to be very big because there's not much time in between charge states. Okay, another thing what that brings up is over here, since it does, these bridge rectifiers have to wait for the voltage here to get higher than what the DC voltage is here to conduct those diodes. You get a big pulse of current, then a long dead spot, then a big pulse of current, then a long dead spot. So you get these huge pulses of current and then nothing. Down here, you're getting pulses of current constantly. Just, you know, I mean, just lots of them. So you don't need a big well. You just need a smaller bucket and throw these old Dixie cups of juice in there. So this guy doesn't have to be very big. All right, another thing. We're going to have a bulk capacitor out here for our rail that would match this guy. Well, and I mean, these caps have the same story I'm talking about. Okay, that brings up another plus for the switch mode power supply solution. Up here, often, like in audio amplifiers, we don't regulate the output because, again, that's going to create dissipation, big parts, you know, just more big stuff. Which means we have to provide even more power at the input because now we're dissipating even more power throughout the power chain here. Well, down here, you can have feedback and regulate this guy very easily because there's so many pulses happening so often that you can say, hey, the capacitor's draining, I need a little bit more. So they give it a little bit fuller Dixie cup that time. And so they keep that thing charged up. And then it says, oh, I'm good. So then the guys with the Dixie cups fill them up with half water and half the juice. And anyway, you see what I mean, is that with the regulated power supply, even if you do a linear power supply with the capacitor on the output of a linear regulator, that linear regulator, it's gonna have a pass element that's gonna keep that capacitor on the output just charged all the time. So you don't need a gigantic capacitor because a linear regulator is going to make sure that that thing's charged. It's holding, you know, solid. So there's some benefits of the AC. Now, as far as this boost converter, the way it's working versus the dead time, the big pulse current up here, over here, this guy, what his job is to take slices of current as that voltage comes up. And then he takes more current, and then less, more, less and less. So when you average the current that he's taking, it's following the voltage wave shape. So that's how you get the power factor correction. It's kind of operating like the Class D amplifier would. How it recreates a wave shape, and then you use some filtering to smooth it off. It's kind of a similar thing. So it's just creating a 60 hertz or 120 hertz pulsating current waveform. So the current waveforms, it's going to look kind of like that once it's over here filtered. And that's one thing I didn't show in either one of these. There's an AC, you know, there'd be an input filter if you're building this for, you know, commercial reasons and that. You'd have to have a filter out there. All right, guys, let's jump over here to the bench and... Alright guys, so let me just show you the eval card for the boost converter. This is something I got from I got both these from Texas Instruments. Okay, they gave them to me for free. Maybe just as much because I'm a power supply engineer. I probably would have got them just for that reason. But they did actually know I was going to make videos, so I think they're happy to give them to me. And then I've been sitting on them for a while. This one actually I made a video some months ago, back a while ago, and since then I started a new job and everything. I kind of got derailed there for a little while. My plan was to build an audio amplifier and possibly using GAN, okay? But I wanted to start with this and kind of move on. Anyway, so back to this. Here's the boost. This is the EMI filtering on the input, okay? Just some filtering, combo, choke, fuse, stuff like that. On the output, we have the bulk capacitor, the boost inductor, and the boost diode and boost transistor on the heatsink. Up here is the bridge rectifier. It's on the heatsink. I'm going to show you guys close-ups of this, okay? All right, so now this is a really cool board. This one here is the LLC design. This is a converter that's become popular in recent years. Televisions and a lot of commercial power supplies are designed with these now. This is a form of a resonant converter, which means it's kind of a soft switcher. Usually switch mode power supplies are what we call hard switchers. They turn on and off, and the voltage and current may not be at zero at that time, and so you get power dissipation on your transistors at switching losses. These soft switchers, you either try to get the voltage or the current near zero when it switches, so that you're not getting the volts across the transistor at the same time you have current going through the transistor. You want it to switch on and be on before you get current going through it. So it makes it more efficient. All right, and this guy here, another TI, and this section right here you would not need because it would be provided on the boost circuit, but to operate by itself they had to put it on the circuit card. You have your input bulk, again that would be on the other card, so you wouldn't need that on this card as well. And then you have your isolation transformer, and this is output diodes. This board and the output capacitors here, see there's not that big for this guy's capable of 15 amps at 12 volts, so he can put out some power. The boost over here can put out even more, like 380 watts I think it is. Okay, switching transistors on the back side of this one, and the controller is right here on the back side. See, that's right over in this section here, right in the front end of the transformer. Now just go over here real quick. Over here, the control chip right underneath the switching transistor, right in that area, right where you want it, real tight and close. Okay, so on this guy, when I flip over, there's a region right through here where you have your isolation from your secondary power to your primary power. See this primary side right here, power coming in, secondary side. So there's a couple opto couplers down here for isolation. So I'm going to bring you over here to the bench, and we're going to look at these a little closer. I'm going to show you some schematics, and we're going to jump into look at some signals. And we're going to look at the switching nodes on each one of these guys, so you can kind of see what that looks like. All right? Okay, let's do it. All right, as I said before, I've made a video on this, but I'm going to go real quick, the boost converter section, okay? AC power comes in, fuse, combo, choke, some EMI stuff, rectifier, and then a small value capacitor, so it's still just pulsating DC at this point. Then what we do with that is we use this control chip to run this transistor, turn it on and off, and boost the voltage using this inductor and this diode, and boosting the voltage up here to about, close to 400 volts, 390 volts. This diode is activated when power first comes through. It kind of jumps over, leapfrogs these two things, and charges this up to the peak value of the AC over here. So let's say it's 120 volts coming in. We're going to have not quite 170 volts probably here, the pulsating waveforms, and that will go through this top diode, charge up the cap. So it kind of pre-charges this before this guy really kicks on and starts going. And then our boost inductor, our boost diode, and our boost FET get controlled by this guy. And we're going to put 12 volts here to run the thing. And then we'll run our second converter on the output right here. And we do have the large bulk capacitor right here. Alright, and then Texas Instruments gives us a setup guide here. Here's the board right here, the heat sink, the input inductor here, our boost inductor here, and our boost cap here. And the transistor and diode are right here on the heat sink. So the diode's here, the transistor, and this is a bridge rectifier, all on the heat sink. Okay, so it's designed so you can blow air across this way and keep all these things cool. So if you have a power meter, which we do, we'll have it at the input. Our AC voltage comes in here, put 12 volts here, and we'll get our output here. Right now, we're going to first test it with electronic load, just like they show. We're going to have a voltmeter here, and we'll look at the output. And yeah, let's do that, and I'll show you the setup. Alright, so this is a quick look at our setup. Our card's right here, the heat sink. You know, it's laid out just like the picture. 12 volts coming in here, and AC running in here, this black cord here. And let's see, there you go, get that out of the way. And so this meter here is looking at the voltage on the load, but so is this meter. I was using them for different things anyway. Right now they're both connected to the output, okay? This one's connected to the load, this guy's connected right here at the output. Also, what we have connected here at the output is these two leads go to the load over there. We have a current clamp on right here, and you see the orange wire down there? You see the orange loop right here? That's a wire I added so I could put this clamp on. So I lifted the leg of the boost inductor so I could put the clamp in there. Like I said, my other video shows all this. Okay, so this meter right here is connected right here. This differential probe, we're looking at the switching node right here on the diode, okay? And this differential probe, of course, we're looking at the output here. So I just put this up here just to show you. This test point right here is where we're looking at the differential probe. So we're going to see this guy, the switching node, pulling up and down, and we'll see the current going through the choke, and we'll look at the voltage on the output. Okay, and for the scope connections, on channel 1 I have the differential probe looking at the switching junction. Okay, right now I'm not using channel 2. Channel 3 is the differential probe on the output, and channel 4 is the current probe. Alright, and a quick look at the amplifiers for the differential probes and the current probe. The MixSig DP10013 is the one that's on channel 3 looking at the output. This guy here is channel 1, and it's the Pintec DP25, and it's set at times 200, by the way. This one's set at times 500. And then the current probe is set at times 10 for 10 amps, and it is the CP2100B. So that's the 3 probes. Okay, and this is the MixSig, and right here, channel 4, the current is in the center of the screen. It is 500 milliamps per division. Here, let me turn off the zoom for now. So that's out, guy. And then channel 3 is sitting right down here, and it's 50 volts per division. That's the output. And channel 1 is at the bottom of the screen, and it is sitting at 100 volts per, and that's our switching node. Okay, I'm going to go ahead and apply power. Now, we've got 12 volts DC running to the converter. So once I turn on power, you'll see everything kind of pop up and go into action, okay? Alright, I moved the camera over just so you could see this guy and watch the DC voltage pop up. Alright, we have action. Okay, I'm going to go ahead and freeze it, and then we'll turn it off. So that way I can reach over here and play with things without worrying about the circuit below me. Okay, you can see it's pretty busy. But you can see the green waveform kind of pulsing like this, and the yellow one pulsing as well. Alright, so what I'm going to do is hit the zoom button, and that little section right there has zoomed in, which is this. So let me move it over towards the center of that guy, and you see that, and then I'll squeeze that in a little bit. Okay, and then I'll just zoom in, and there you go. So the current rise fall through the inductor, and you can see this is the switching node, so when it's down, that's when the FET is turned on, pulling itself down to ground and pulling current through. So the current ramps up to the inductor, then it turns off, the voltage bounces up, and remember this is 100 volts per division, so this is pretty close to 400 volts right here, amplitude 402 volts it says. So it comes up to here, and then the current drains out of the inductor through the diode and goes to the output. And then what happens is that switching node, the inductor is empty. I got it running dry, and so then it kind of resonates a little bit. So as we increase the load, then this triangle will come down where the next one goes up, and this current will stay above zero, and we won't get this. So right now we're running discontinuous down through here, and if we run continuous, you'll see a cleaner waveform. Now if I come over here to the kind of the edge of this, sine wave, so this is how the sine wave's coming through, and it's taking slices of current all the way across. Alright, sorry, kicked the tripod. Alright, well, so yeah, as we come down through these other spots on the curve, if I move this around, you'll see how as I drop down one side, you'll see how that changes a little bit. Like right there, you see how that looks like it's pretty continuous. The current is charging this whole time, drops down a little bit, and then charges this whole time, drops down a little bit. Now if I go to, say, the other side, you should see just the same kind of thing happening right there. And then just during the middle, when the voltage is at max, that's where we don't stay on as long. And so we charge up for a little bit, we discharge, and then there's some ringing. Okay, that's just the discontinuous mode. And you can see the voltage up here, the output voltage, and it's 386 volts, almost 87 volts, and there's just a little bit of noise on these switching cycles. So this is at a light load. Alright, let me show you what this cool redfish meter, power meter, it's a clamp on, tells us. 43.6 watts, 120.8 volts in, 384 milliamps. So there's our power, voltage, and current. Okay. Now this is our VA, 46.4. So almost the same as the power. That's pretty darn good. And this is why power factor is 0.938, so it's 0.94. There's only 16 VAR. So with all that power, we only got a little bit of reactance power. Okay, and the phase between the apparent power and the real power is only 5.9 degrees. So pretty nice. Nice power factor. And this is a light load. It should get better with higher load. Okay, what we're going to do is we're going to turn it on, and then we're going to bump up the load. Okay, there. See, what we're looking for is we want to see when this stays continuous, where that light's triangular. Okay, here, let me turn on low. It's going to get a little loud. There we go. Okay, I just turned on about 28 more watts, something like that. Okay, I'll go ahead and freeze this. All right, let's take a look at this meter again and see what we get. We got 67.3 watts, 118.9 volts in, and 572 milliamps. And look at that, 68 watts. So pretty darn close to the, 68 VA, very close to the wattage. So look at that, the power factor is 0.99, that explains it. the VAR dropped all the way down to 9.4. So, I mean, it is getting pretty close to unity. The angle is 10.5 degrees. It's looking pretty darn good. Okay, now that we know that this guy's working well, let's power up the other converter. Okay guys, so now this is the isolation stage. There's our isolation transformer. This is the DC to DC converter. So we got our high voltage coming in here, about 389 volts, 390 volts. And then we have our two switching transistors here. We're going to be monitoring this point, and then they go through this primary side of the transformer. The other side of the transformer is connected to these two capacitors. It's kind of a capacitor divider. So virtual, ground, if you want to think of it that way. So these guys will be switching. This guy will pull it down to ground. This guy will pull it back up to 390 volts. And this guy will kind of sit in between, held by these two capacitors. Alright, so anyway, this is our transformer. This winding here will provide voltage back to our control chip. These windings here make up the output, which in this case is just a single 12 volt capable of 15 amps. And this is the feedback. This is the isolation, the optocoupler providing isolation to the control chip. Now let's just look at the control chip. So this is the control chip, right? Now that board, what it does is it takes the AC input because it needs to monitor that AC input. Okay. Now if this and the other boost converter were on the same schematic, then of course we wouldn't need all these parts. We just take this from the boost converter. Okay, and so then more feedback here. And sorry, this circuit here is just used to control standby, to shut down the power supply and put it in standby if you want to do that. Alright, so now what you see is the boost converter, right? We still have the 12 volts coming in here. Up here we have the AC. But see, now we have this green and white coming over here to this AC input. And this part of the circuit is just basically monitoring that. So we have our bridge rectifier, capacitor, and some resistors to put a really light load. This is just for monitoring AC. Like I said, if all this circuit was on that card, then this stuff would not be there. Two diodes would be, but otherwise all this stuff would go away. Alright, so our switching transistors are underneath the transformer down here with our controller on the other side of the board. Okay, so what I did is I moved the differential probe to this switching node right here, and this is the return side right here. These are our rectifiers for our output and output capacitors and our output voltage, the 12 volts here. Right now there's no load. We're going to just power it up with this guy, no load, okay? So when I switch power on, it's going to start the boost just like it did before. But right now the only load is, here's where the load was connected before. Now it's come over here as the input voltage to this. And the way we had to do it is minus had to cross over because minus is down here. And then plus had to cross over because plus is at the top over on this side. And by the way, this AC, this white one's a neutral. And so I have the two neutrals tied together just to make sure that when, I don't think it matters, but I just did it so that this AC is in the same phase as that, okay? Alright, and then I have this meter here. I'll just bring this over here in the picture so you can see that this guy here is going to be looking at the voltage here on the output. Alright, now channel 1, the yellow one, is still connected to the switch node, so we should still be watching the switch node. Channel 4, the green one, is still connected to the current, so we'll still see the the current, this triangular wave shape. What's changed is channel 3, we're not going to be looking at the output 400. Now we're going to be looking at the switching node of the new converter. So we'll be able to see this guy switching and the new converter switching node too. So we'll have this switching node and the purple one will also be a switching node. Okay, for the reference position for both of them is right down here in the lower corner. Okay guys, I think we're ready to go. I'm going to hit the power switch. Okay, there we go. Let's increase the load. There we go. We're increasing the load. It's looking better, I think. Okay, I'm going to freeze it. And let's just turn it off. Well, that's definitely continuous. That's, wow, it's interesting that the frequency is pretty darn close between the two converters. Alright, so there we are, and see, we're right here. It looks like we're... Okay, let's move this over right in the center. Yeah, there's a continuous operation, so that's pretty nice. Now, the purple one, all we're going to see is kind of boring. It's just a, 50% duty cycle. It's, going almost 400 volts peak to peak. But you can see the power factor, the current's being taken in a whole bunch of slices in kind of a pulsating AC waveform, sinusoidal waveform. So that's at the top. Let's go to the falling edge of this green one right here, and still looks good. You'll see the duty cycle changing and stuff, but now I'll go to the other side. Okay, up towards the middle, yellow one, duty cycle's gotten fatter. Okay, then I'll go to this other edge. And you can see the duty cycle got narrow again, but that looks pretty good. Alright guys, I hope that made sense. I hope it was helpful just to look at some things. Now the one thing, as we looked at the switching node on the LLC, it was just a square wave. Because it's because... And that's because it's kind of operating as a chopper, and then there's a resonant frequency going on, and you can set up the resonance to kind of work with that chopping action. And operating at 50% duty cycle, just on off, it makes it efficient to do it that way. And anyway, I'm going to show you how this thing works in another video. But I just wanted to demonstrate this today just to kind of give you an idea of the pieces of the puzzle, okay? I hope that made sense. Hey, give the video a thumbs up if that helped you. It helps the video a lot to do that, and appreciate it. Appreciate all your comments, and I want to thank the Patreons for all their support and everybody else for watching the videos. And all right, guys, we'll see you next time.